Okay, so in this example problem here, we're going to design a low-pass filter that has cutoff frequency of 8 kilohertz, and it specifies using a resistor of 10 kilo ohms, and then it also is wanting to know what the magnitude of h at j omega is in decibels for 4 different frequencies. Now, the one thing we have to keep in mind here when we do a design is, well, there's two things. One, we have to be able to draw the circuit, but the other is um, what are the units given to us? And what do I mean? Well, we know that omega c is equal to 1 over RC as the cutoff frequency, but these units are radians per second. And what we were given, though, actually is a cutoff frequency of 8 kilohertz. Don't know where 2 came from, which of course is in units of 1 over seconds. So we have to make sure that we convert things properly. But now this isn't a big deal. Omega c is just equal to 2 pi fc. But this is very important that you want to always remember that. So what we have here, if I look at this here to figure out what the capacitor value is I just have 2 pi times 8 kilohertz is equal to 1 over 10 kilo ohms times my capacitance. So quick solving for this gets me 1 over 10 kilohertz, or 10 kilo ohms times 2 pi times 8 kilohertz. And then if I do that real quickly on my calculator, I get 1.99 nanofarads. Which we could, of course, probably round this if we wanted to 2 nanofarads if we wanted to. Now, we also then have to draw the circuit. Now, it's a very basic circuit, but you need to make sure to have everything labeled. Vn. This would be, resistor was 10 kilo ohms that was specified. And this is 1.99 nanofarads, or 2. You could write either one, would be fine. Now, if you leave your circuit like this, you will still lose points, because to mark this, you have to mark where the output voltage is being taken. So I need to mark that the output voltage is across the capacitor. So this is my low-pass filter that has a cutoff frequency of 8 kilohertz. Now we're going to compute here magnitude of h at j omega in decibels, which is going to be, well, remember here, before we do that, let's remember that my general transfer function was h at s is equal to omega c over s plus omega c. So my transfer function is 2 pi times 8 kilohertz over s plus 2 pi times 8 kilohertz. Now you could go ahead and just simply go ahead and write h at j omega is equal to 16 pi k over j omega plus 16 pi k. And then go ahead and substitute in a value for omega, and then go ahead and find the magnitude of it once you do the divisions with your calculators. But I'm going to go ahead and just write this in the form here that we know then that the magnitude of h at j omega is equal to 16 pi k. And the reason I'm writing it in terms of k is we're going to see something nice here in a second. Omega squared plus 16 pi k squared square root. But what I'm going to be able to do is notice that omega is going to be in kilorads per second as well. So I can really rewrite this as just 16 pi over the square root of omega squared plus 16 pi squared, knowing that omega is in kilorads per second. So let's go ahead and do that. I'm just going to make a table here. So we have my frequency, and we had 1 kilohertz, 8 kilohertz, 80 kilohertz, and then 800 kilohertz. And then I'll have h at j omega magnitude, and then I'll have h at j omega magnitude in decibels. And I'll do one computation over here in red. Okay, so let's do one of the computations here. So magnitude of h at j omega, so magnitude of h at j times 1 would be 16 pi divided by the square root of 1 plus 1 squared plus 16 pi squared. So if I do that computation on my calculator here, (16 times pi squared plus 1 square root), you get 0.9998. So we get 0.9998. And then to do this in decibels, magnitude of h at j omega, or j times 1, in decibels would be 20 log of 0.9998. So let's do that. 20 log . And you get negative 0.0017 decibels, which is essentially 0 decibels. And remember, 0 decibels is unity gain. So we're getting 0 decibels, or in other words, we're getting unity gain. Alright, so now I'm going to pause the video and just do these computations and write in the rest of them here, and we'll talk about it for a second after that. Well, and I just realized I made a mistake here as I paused the video. I said be careful of your units, and the first thing I did was not be careful of my units. This is in kilohertz, so this should be the square root of 2 pi times 1 squared, which if I do that, it's going to change my answers a little bit, and I'm going to pause the video, correct those answers, and then you'll see all the answers for the rest of them. And so for here, before I pause it, so the next one would be, if we did h at j8, it'd be 16 pi magnitude of this over the square root of, and actually we could make things nicer and factor out some pi's and whatnot, but this would be 2 pi times 8 squared plus 16 pi squared. Okay, so I'll do those computations and fill in our tables. Alright, and so this is the table that I've filled out here. So at 1 kilohertz, correcting the mistake, we get 0.9922 as the magnitude, and then converting to decibels, negative 0.068, which again is essentially 0 decibels. Moving down, at the corner frequency, 8 kilohertz, which is what we designed for, or the corner cutoff frequency. We designed it to be there, and as we can see when we plugged in, we get 0.7071, which is 1 over square root of 2, which corresponds to minus 3 decibels. And again, that corresponds to the half power. But then we're seeing a pattern here. At 80 kilohertz, I have minus 20 decibels, and at 800 kilohertz, I have minus 40 decibels. And you might be able to take a stab at what you might think you're going to get at 8,000 kilohertz. And if you think about this for a second, your guess would probably be minus 60 decibels, and you would be correct. And this is what we mean by when we say a slope of a decibels per decade. Because if you think about it, when we've reached into the quote linear portion of this filter, it's decreasing by 20 decibels per decade. Because going from 80 kilohertz to 800 is a decade increase multiplied by a factor of 10, which is a decade, and we get a 20 decibel decrease in there. And if we go back to our example here, it's not necessarily clear here. It doesn't look like quite like a straight line here, but we can kind of see there's these what we call kind of linear portions here, where it looks like it's going just as a straight line down here. And in fact, all of the orders of filters, I just hit the wrong thing. All the order of filters have that kind of linear thing here. It's just about how quick is the decibel per decade. You might say, well, this doesn't even look like it's in decibel. This is a normalized graph, which, you know, I'm not going to go into the details of what a normalized graph looks like or anything, but the whole idea is that this decibel per decade idea you can kind of see coming out in these computations. So believe it or not, that's all there is to low-pass filters right now. We are going to move on to high-pass filters, which are going to be about as easy. And then we're going to move on to some discussion of bandpass filters and different ways to build bandpass filters. And then I think we will see here. We might talk about a few higher order filters right now, or we might move on to active filters. I'm not sure. I haven't decided yet.